Hey everyone, today we'll be deriving the Bogoliubov transformations, so let's begin. So we've seen in our past videos of quantum field theory on curved spacetime that we are able to expand our quantum field in terms of different mode functions, right? We can have some coordinates t and x and some coordinates t prime x prime, where x t and x prime t prime are related via some diffeomorphism, some coordinate transformation, and as a result, the field will be decomposed in a different way. And as a result, they can be a different notion of a number of particles depending on which basis we choose. So the Bogoliubov transformation is actually the relation between the creation and annihilation operators in the old basis with the creation and annihilation operators in the new basis. And that's the goal of today's video, to actually derive that transformation. To do that, we first use something called the inner product of our fields. And this particular inner product is very useful for us. I think it's technically called the scalar product, but I'm just going to call it the inner product. And it's very useful because it allows us to extract our coefficients. So for example, with this definition, phi and uk, once we put this into this relation over here, it will extract a of k. So that's why this particular relation is pretty useful. So let's actually prove that right now. So here's the formula for the inner product. I went ahead and used a dummy variable k prime. We're going to see that k prime equals k in the end. So we're going to use k prime for use momentum for now. So what we have to first think about is, what is the time derivative of phi going to be equal to? Well, we know that phi is just going to be the superposition of our plane waves, right? And for context, UK is being defined as 1 over 2 pi cubed square root of 2 omega k, and then e to the minus I k mu x mu. It's just a shorthand way of writing that. So the time derivative of phi, well, we know that the time derivative of u of k is going to be equal to minus I k naught uk. And that this will give us a contribution of I k naught. So this means that we can just factor out the I k naught in front of that phi. So basically what I'm saying here is that we can just say that the partial t of phi is just going to be I k naught times the integral over the momentum. So now what we want to do is find partial t of uk conjugate. And we've already found that. That's just I k naught of u conjugate k. Actually, remember that we were looking at k prime, right? So technically it's I k naught prime u conjugate k prime. So essentially this is going to give us a contribution of I k naught prime. This will give us a contribution of a net one of I k naught. So we can do what's called abuse of notation. Let's just kind of pretend that k naught equals k naught prime in the end. So we're just going to factor out all of these together in the front. As a result, these i's will cancel out, and we have a factor of -1 in the front. This basically means that phi and uk prime's inner product, doing that gives us minus k naught integral over this. And then now we can actually expand these out. This is 1 over 2 pi cubed square root of 2 omega k e to the minus I k mu x mu. And then u conjugate k prime is 1 over 2 pi cubed this, and then e to the I k mu prime x mu. So this means that u conjugate k prime is going to leave us with 1 over 2 pi to the 6th, and then 2 omega k e to the minus I k mu x mu e to the I k mu prime x mu. So then we can just rewrite this out as I times k mu minus k mu prime, and then x mu. We can do similar things with u conjugate k prime. That's going to give us 1 over 2 pi to the 6 to omega k e to the I k mu plus k mu prime x mu. And we are going to be left with that this is minus k naught integral over the volume. So we can look at which terms will cancel out with which terms. So here we have an a conjugate k term. Here we have an a conjugate k term. It's the exact same term. Since there's a subtraction sign, that means that these terms are going to cancel out. And since we have this negative term here, subtracted with the exact same term here, we're going to end up having a minus k naught this, and then 2 times ak 1 over 2 pi to the 6 to omega k e to the minus I k mu minus k mu prime x mu. So that's our answer for now. Of course, you have to integrate that over k. What we can do here is, that should be a negative 2 actually, and that will cancel out with this negative, giving us a positive. This is going to be a delta of k mu minus k mu prime when we integrate it over that position over here. So this means that we are going to have k naught times the integral of dk 2 of that, and then ak 1 over 2 pi to the 6 to omega k. And actually this is going to be 2 pi cubed, right? Times this delta function. It's just like integrating over the forward position. So this is going to give us a factor of 2 pi cubed delta of k minus k prime, or k mu minus k mu prime. And then times, actually, yeah, that's just it. And then now we can integrate this over the momentum. We know that this will cancel out with this, giving us a factor of 3 here. So technically speaking, we kind of like did some things a bit too early. So like we would have had 1 over the square root of 2 omega k, 1 over the square root of 2 omega k prime. We would have had that. So here, for example, we should have had this should have technically been square root of 2 omega k, square root of 2 omega k prime, but we just got already combined because we knew like in the future that they would be equal to each other. So we would have had that left over, but we just kind of went ahead and just called it 1 over 2 omega k, right? But basically, if we were to like be more correct, we would have this as a result. Then doing the integration, I'll give us ak 2k naught, and then 1 over 2 omega k. These 2's will cancel out, and we are left with a k naught over omega k. And we know that k naught is just equal to omega k, right? So these go away, and bada bing, bada boom, we have proven this relation right over here. Cool. And using similar arguments, we can show that v of p with uk is going to be gamma kp, and then v of p with u conjugate k is actually going to be equal to minus beta kp. And that's for this over here. So this gives us a direct way of calculating the Bogoliubov coefficients. And those are what these are, if you guys didn't know. In most references, you will see the first Bogoliubov coefficient being actually written as alpha kp. I did not want to do that because here we have a of k, then here we have alpha k, and a and alpha look pretty similar. So I'm just going to use gamma of kp instead. So cool. So now we have a way of calculating those coefficients, and now what we want to do is write out a of k and b of k, sorry, a of k and a conjugate k in terms of b of p and conjugate p. So essentially, what we're saying here is that if a vector can be written in terms of, say, a basis, so like v1 and e1 plus v2 and e2, and then it's written in terms of a separate basis, so that will give us, say, I don't know, c1 e1 tilde plus c2 e2 tilde, and it's the same vector being written in two different bases. This implies that e1 and e2 can be written in terms of e1 tilde and e2 tilde. You can show this better by using tensor calculus. So we know that partial r over partial pa is just partial ci over partial pa, partial r over partial ci, where this is just the new basis vector, right? And this is the old basis vector. And this over here is going to be a matrix. Let's call it A, I, A. And this is going to be what's called the Jacobian, by the way. So this is the Jacobian. And this relates the new basis with the old basis. So that's why we see two components, K and P here. Because in the Jacobian, we're going to have I and A, two components. And this, technically speaking, is a sum over I. And the reason why we have 2 over here is because, like, U1 and U2 and so on does not encapsulate U conjugate K, if that makes sense. So we have to have a separate one for U conjugate K as well. I hope that makes sense. So we can just plug in V, expanded, we just plug that here into phi, put it in this inner product, and that's going to be equal to A of K. So basically, we want to plug in this inside of this, and then this inside of this, and then take the inner product, and that's going to be this over here, and that's going to be equal to A of K. So we've related A of K with B of P and B conjugate P, essentially already. And all we have to do is just expand that by taking that inner product. Inner product. And if you were to actually do that, you would actually get this right over here. And this is the Bogoliubov transformation with A of K and B of P. So yeah, that's how you actually find out, or that's how you derive the Bogoliubov transformation.